Okay, let's talk about machine learning. You hear this term thrown around all the time, right? But what is it, really? What's actually going on under the hood? Well, that's exactly what we're going to unpack today.
And you know what? We're going to start with something a little controversial. This quote from Andrei Burkov. Let's start by telling the truth. Machines don't learn. Whoa. Okay, so to really get what machine learning is, we first have to tackle what it isn't.
So, yeah, that's the big secret. Despite the name, machines aren't learning like we do. Not even close. Think about it. If you learn to play a video game, you can still play it if someone, I don't know, tilts the screen, right? You adapt. A machine learning model? Nope. It would totally freak out unless it was specifically, and I mean specifically, trained for that exact tilted screen scenario. The term itself, machine learning, actually goes way back to 1959 at IBM. And let's be real, it was fantastic marketing. Okay, so if they're not learning, what in the world are they actually doing? What's the trick here? Let's pull back the curtain. This is it. This is the big reveal. What we call learning is really just finding a mathematical formula. That's it. It's about building what's called a model. You feed this model a mountain of data, it crunches through and finds the patterns hidden inside. And then it uses those patterns to make educated guesses or predictions about new stuff it's never seen before. It's incredibly powerful for sure, but it's just math. It's not magic. All right, that might still sound a bit abstract. So let's make it super concrete with an example you and I use literally every single day. The good old spam filter. How exactly do you teach a machine to spot spam and keep it out of your inbox? Well, it's kind of like a four-step recipe. Step one, you need ingredients, right? So you gather a ton of data. We're talking thousands and thousands of emails. Step two, you need a teacher. A human has to go through and label every single one of those emails as either spam or not spam. This is the supervision part. Step three, computers don't read words, they read numbers. So you have to convert all that text into a format they can understand. This gives you a feature vector for each email, which is just a fancy way of saying a list of numbers that might represent things like, how many times the word free appears or if there's an attachment. And finally, step four, you feed all of that neatly labeled numbered data to an algorithm, and its entire job is to figure out the mathematical pattern that tells the spam apart from the good stuff. And here's the coolest part. At its core, the algorithm is basically just trying to draw a line. Seriously. Imagine you plotted all those emails as little dots on a giant chart. The spam dots are in one corner, the not spam dots are in another. The algorithm's only goal is to find the best possible line. They call it a decision boundary, to separate the two groups. Once it finds that line, any new email that comes in gets plotted, and depending on which side of the line it lands on, boom, it's either spam or it's not. Okay, so that whole process with the spam filter, where we had a human labeling everything, that has a name. It's called supervised learning. Makes sense, right? There was a supervisor. But that's not the only game in town. There's another whole style of machine learning. So let's zoom out for a second and look at the two big categories. And here they are, side by side. It's actually pretty simple. With supervised learning on the left, you've got labeled data. You've got a teacher showing it the right answers, and the goal is to make predictions, like our spam filter. But on the right, you have unsupervised learning. And here, there are no labels, no teacher. You just dump a bunch of data on it and say, find something interesting. Its goal is to discover hidden structures all on its own. A classic example is grouping customers. You might not know what your customer segments are, but an unsupervised algorithm could find them for you. So building these models is obviously super powerful. But there's a catch. A really common trap that you absolutely have to know about. It's what happens when a model gets, well, a little too smart for its own good. The problem is called overfitting, and the best way to think about it is with a school analogy. Imagine a student who's cramming for a test. Instead of learning the actual concepts, they just memorize the exact answers to the practice questions. They get an A+ on the practice test, right? But then the final exam comes along. The questions are worded just a little bit differently, and they totally bomb it. Why? Because they memorized. They didn't learn. A machine learning model can do the exact same thing. So a good model, a well-fitted one, does what you want it to do. It looks at all the training data and learns the general trend, the big picture. It sees the main pattern and ignores all the little random blips and noise. But an overfit model? Oh, it's a perfectionist. It tries so hard to be right that it ties itself in knots, trying to perfectly explain every single data point it was trained on, including all that random noise. And the result? You get a model that looks like a genius on the training data, but is completely useless in the real world.
And that failure can be absolutely critical. We're talking about a self-driving car that fails to see a new kind of stop sign, or a financial model that makes a catastrophic prediction because the market did something slightly unexpected. It's a huge deal.
Okay, so we've covered a lot. But if you're going to remember just one thing from all of this, what should it be? It's this. Machine learning isn't what you see in the sci-fi movies. It's not about building a conscious, thinking mind. It's a practical and, yes, incredibly powerful tool. It's the science of using data to find mathematical patterns, patterns that can then make some seriously powerful predictions to solve real problems. So the recipe is actually pretty simple at its core, right? You've got data, an algorithm, and a search for a pattern. But the things you can build with that recipe, they're pretty much endless. So the real question I'll leave you with is, now that you know the secret sauce, where is this incredibly powerful tool going to pop up next?